only one section. All right. So any other homeworks to come in? All right, so I will grade those over the weekend, and then we will talk about them on Monday, so we can talk about things that people might have had trouble with. But any burning questions that will stop you from having a good weekend if we don't talk about them now? Yeah.
So, what are the tuples that you get from a cross product? Are those ordered necessarily?
Those are ordered, yeah. Tuples are an ordered pair or an ordered triple of things, so that's why they go in parentheses instead of curly brackets. Exactly.
Should we include null coordinates too in that assessment?
So in general, if you have something like the set S equals heads comma tails, those are curly brackets, right? So H is an element of this, T is an element of this, but the empty set is not a member of S, right? There's no empty set inside here. So that would not be one of the things that you cross with another element from another set. But if, you know, our set consisted of, say, H and T and the empty set, then yeah, when you took the cross product, you'd have something where the first element was the empty set.
Okay.
So that's one of those moments where, like I said, sometimes you need to not think too deeply about it. Because if we think more deeply about it, we know the empty set is a subset of this. And that can start us thinking about, well, maybe the empty set should be included in there, right? But you can usually, with logic, with mathematics, take things extremely literally, right? And there's two things in here, this and this. There's three things in here, this and this and this. And not worry about this happens to be a set, and it happens to be an empty set. So that's always a potentially confusing. So thanks for asking that. Other things? I can take it. Everybody get a chance to sign in?
I want to ask you one more question.
Yeah.
On the homework, it was like asking like for the infinite U.
Mm-hmm.
It was problem 6.
Problem 6, yeah.
And it was like the what are the answers or logic behind the problem for that?
So let's pull it up so I don't try to remember it. So I think it was 1.3, no, 1.2, question 6.
Was it the complement of the infinite set?
Yeah, the
Yeah.
infinite and finite things.
So suppose U is an infinite universal set, and A and B are infinite subsets. Answer the following questions. Must the complement of A be finite? So let's play with this. So U is infinite. And I don't know if we've said this formally, an infinite set is a set containing an infinite number of elements. And we haven't described exactly what infinite means, but it's more than any number. It's more than a million, it's more than a skrillion. There's no bound on how many elements. So U is an infinite set, and what did they use? Let's use A and B. So A and B are infinite, but presumably smaller than the whole universe. So question A says, look at the complement. Does that have to be finite? So what do you think about this? First of all, could the complement be finite?
Yes.
What would be an example? You're right, it could be.
Complement of U itself.
Yeah, A could be the whole universe. That's a subset of the universal set. And the complement of the universe is the empty set, which is extremely finite because it has 0 things in it. So it could be finite. Does it have to be? Right? So what's an example where the complement would be infinite?
It's every other number, there's some formula.
Yeah, perfect. So U could be the set of all integers, and A could be the set of even numbers, and A complement would be the set of odd numbers. And A is certainly infinite. There's an infinite number of evens, but the complement is also infinite. So taking away from an infinite, even if you take away an infinite amount of stuff, you might still have an infinite amount of stuff left over. And this is going to play in really nicely after break. We're going to go into story time. And I'm going to tell you a story about infinity and parallel universe and aliens and Hilbert's Grand Hotel. And we'll be looking at this kind of thing. What about A union B? Must that be infinite if A and B are infinite? So A is infinite and B is infinite. We're going to union them together. The result is also going to be infinite, because it's going to have everything that A has, which is by itself an infinite number of things. And it might even have more stuff from B. Mm-hmm. Okay, so the union will definitely be infinite. What about the intersection? Right, and we got a good example right here. If A is a set of evens and B is a set of odds, that intersection is empty. That's very finite. Or this could be numbers bigger than or equal to 0, numbers less than or equal to 0, and the intersection is a singleton set, just containing 0. So this exercise is really just kind of about starting to think about infinities and the fact that they don't really work the same as very big things. If you have a very big thing, the complement is usually a very small thing. But infinity is such a big thing that it gets weird. All right, cool. So I want to talk about a few more. Well, I want to talk about the power set. Did we talk about the power set yet? I don't think we did. I think I alluded to it. Let me talk about the power set, and then I'm going to have you go onto the board and work on some problems from here. And then I'm going to have you work on a disturbing problem called Russell's paradox. And that'll take us up to a break, and then we'll go ahead and we'll talk about infinities. So let me talk about the power set. And this is another one of these things that's a pretty simple definition, but using it can be complex. So let S be a set. And usually this will be a finite set. So P of S is what we call the power set. And this is the set of all sets A such that A is a subset of S. So the power set of S is the collection, or the set, of all subsets of S. So how much trouble could that get us into, right? It's a very simple definition. So let's look at one specific example, and then I'll let you work on some problems with this. So suppose S is, let's make it a set with two elements. So somebody give me an element. X, okay. Somebody give me another element for our set. Square. All right, there's a perfectly fine set of two elements. So let's list some subsets of this. You did some of this in the exercises on Wednesday. Shout out some subsets.
Null.
The empty set, null. That's one subset. What's another one?
X.
The set consisting of just X, the singleton set. Say again? The set consisting of just a square. Any other subsets?
X and square.
Yeah, I drew a comma, so there must be one more. The set itself, which is always a subset. Any other subsets? So this collection of four things, we can turn that into a set. That's the power set of S. And it's a set containing four elements. And those four elements happen to be sets themselves, but that's okay. We've pretty much said sets can just be collections of whatever, just things. So that's what the power set looks like. So I'll give you a handout with a series of questions. We're not going to do all these questions. Let's just work on a subset of these questions? No, sorry. Let's just work on numbers 2 and 3 and 4. And I'm not going to worry about 5 and 6. I'll look at your homework and see what we have to go over with that. Same with number 7. Yeah, let's just work on questions 2, 3, and 4 from this handout. So go ahead and find your favorite group, and I will put these up here. And grab one copy per group, and let's work on those, and I'll walk around and see how you're doing.
What was 6 period?
What would 6 be? I like your different colors. I like your different colors.
Oh yeah, I try to color code a little bit and
I'll give you that.
hopefully get
I'm usually dedicated like that in the interim. For the anyways.
so one.
Okay, we might have room. So 2, 3, 4.
If pen. Number 1, set S, which is
Okay, so that's pretty much.
1, 3, 5. Sorry. Right, the power set.
Wait, no, we're doing 2, 3, and 4.
Oh, 2, 3, and 4?
Yeah. So the set S, if you write the power set of S, we call that a set of integers.
No, a set of integers. Okay, so.
What else equals the set of A over the right, the power set.
Z and Q, right?
I think that would just be null and then A.
Yeah.
Right.
Now, right, the power set of the power set.
The
Okay.
all integers?
So yeah, question 3, work methodically, right? Just follow the definition and try not to look at the weirdness.
What was the symbol for all integers?
Okay, so it's pretty much like
Z.
Oh, yeah.
yeah, and then
Oh, yeah.
Oh, yes, because it's
Oh, yeah.
representing,
yeah.
because this
Yeah.
symbol is representing the set.
Oh,
So it's not a set
Yeah.
with the empty symbol.
Essentially, is a fraction, right?
Yeah.
Okay,
Yeah.
Yeah,
Really good.
So when we put this into a power set, simply
Right, so the power set is a set, and any set you can take power set of.
Just start slowly. So yeah, we'll just write each element.
I'm just do the
And that'd be 2
equal. How did we write it out before? Just as options.
Oh,
There would be null
2 minutes.
So we're gonna do.
Z, in which
Yeah, it's just a,
any
Oh,
real
it would be a lot, it would be a lot.
It's gonna take us
Yeah, I was like,
Yeah.
integer.
Do we have to
So gonna be-
double up the brackets on the
Q.
like this? Do we have to do that?
So this is a set containing one set,
Okay, so
which is a set containing the empty set.
Okay.
And if that's what you mean, which I think it is, then yeah.
Alright. Stick with it then.
So you can assume that you know what Z and Q are, right? Z is the integers, Q are the fractions. And so you don't really need to define those. You can just write a funny Q, and we'll treat that as a set of fractions. And same for Z.
Oh,
Yeah.
yeah.
Yeah, you're right. And then that, and then that. I think that's it. Yeah.
There you go.
So it's going to be these two.
What would be the set, right?
All right, you got one more thing you got to do for that answer to be correct.
So you have another.
Yeah, you have another, you have two more.
There you go.
That's
No,
why it's like.
No.
not quite.
Sure.
There you go. Right, so the power set has to be a set. So it goes in curly brackets. Yeah, that's perfect. Very good.
That's another one. That's those three.
Number 3 now. No, this is just null set. That's just saying null set. Number 3. What the hell is number 3?
Actually, yeah.
That's equals to A, like the power set of S. Like the power set of S. Like the power set of power set.
That's how.
Because it would be a subset. Oh.
So,
Are we?
So subsets of
I think the set of S.
So there's the empty set always. Right? There's the subset containing this element.
power set of S will equal.
There's the subset containing this element.
Oh.
Yeah.
So then this would be
Do you mind if I still the eraser?
the set of.
Good catch.
Yeah.
And then
Power set.
set.
Power set.
Because each of these would be a subset. Yeah, right.
Equal.
Set, set.
Null.
And then,
Power set
and then the
of
last
A.
one would just be.
No, it would be the power set of. Wait, no, yeah, you're right. Yeah, spell that? Yeah. And then,
So it's just going to be this.
And then, yeah, which ones are these are the separate.
And one more.
And then almost perfect. We could do all three.
So there's set A. Okay, so power set is a subset. Well, this is always a subset, right?
no set.
Another subset is S
And
itself.
then.
Okay.
Yeah.
So subsets of this.
Okay, so there's the new null set.
And
the
then
old
we
null
have to
set.
do another one,
That null
where
set.
it's these two.
And then for this one.
So this is the same set. Yeah.
And then this one.
All right. And then there's also.
That's why I put this, yeah, I know.
Now, we get to the fun.
Okay, so we don't have singles, doubles,
Into which we have
that,
A with
that, we need an extra
The
set.
set containing the empty
we
set.
have A with
That's no, that's a set containing one
Oh, we
element.
don't.
It's a little unclear.
Yeah, it's right here.
Right.
And then we have,
So that's one of the.
Now we
oh,
have-
we don't have this.
Okay, and then
power
we're back
set,
to.
power,
So
power
three
set,
for doubles.
Correct.
and then one more, I believe?
Yeah.
And then run two.
Those
The-
four elements. Yeah, yeah, that's different.
So this is
A.
sets of, so this is gonna be sets of three.
Power set,
Okay.
What?
Yeah, one element.
Set
Yeah.
containing
No.
null.
Yeah.
Wait, that's
All right.
No, I already did, okay.
So there's a subset containing this.
Okay, oh yeah, sorry.
There's
We're
a
doing
subset containing one element.
and we're doing number 4 now?
Containing this.
Oh, yeah, so this one
This one is set containing one thing, which is.
Oh,
yeah.
You don't have to do that.
One,
Right, this is
No,
it.
no, it's
seven.
I think I've done the same.
There you go.
So we've got.
Yeah, so that's where it gets really crazy. Right, that's instead of.
So it would all be null.
The don't from thing.
Right,
Oh, yeah.
A is not
It would
actually
simply all just be
so
null.
that's not a subset.
One,
Yeah.
so there'd be one,
Oh, yeah,
two,
so it's
three,
good.
I like this one.
4, 5,
Yeah.
6.
No, because
Oh, yeah,
that,
seven.
yeah, set containing A, that's not a subset. This contains A, but this does not contain A. Right? This is a subset that contains curly bracket A, curly bracket, which does contain A.
So it's still four elements. Alright, so it's just flipping through.
Alright,
Oh, I see lots of brackets.
Yeah.
Oh, yeah. That would be the.
So then we need to do this one. And then I think that's it.
Oh, yeah.
That's all we need, or do we need to continue on?
I think it's pretty good.
We need to check.
Three?
This one.
Yeah, no. It's probably gonna be a work.
That's the one I'm gonna pass on.
I'm gonna forget something when I write that on my test.
Mm-hmm.
Yeah, you forgot it.
Yeah. But the power set is just.
So this is good enough for 3. You missed one here, but I'd rather you work on 4 and you'll pick it up. But let's look at the power set of this. Okay, so this contains 2 elements. So we know the empty set's always a subset. You got
That's right.
that one. We know the set itself is always a subset. You got that one, right? There's a singleton subset which contains this element. Curly bracket A, curly bracket.
This is just sit down.
Right, the set contains
that's
2
what-
things, you can have a
Swift.
subset containing the first thing only. And that first thing, right, the element is curly bracket A. So the singleton set consisting of that looks like that. So that's actually a subset of this. And then the fourth subset.
Should it be in green?
Which is another singleton. Of the null set exactly.
And then will you move
Right, and that's different from that.
Right.
This has no elements, this has 1 element, which happens to be the empty set. All right, so take
You
that.
see me essentially before class from 8:30 to now.
I have a 224 at 9,
Oh.
10. 10 to 11.
It's gonna be a lot of.
Command line argument for OPD 204 or 44.
Yeah.
They showed us making pick up 6. Probably.
Is it? But it's only the first. It's only
Oh,
these
yeah.
2. That's right, yeah.
So I'll have to check out.
Wouldn't this issue still essentially, like, in the end, wouldn't this also essentially just be this?
What, all this, would be that?
And then just take them to that one.
No, it wouldn't.
And you've got the idea, so unless you
Technically,
need to,
what-
you can say, you can. Yeah.
But since these are all the same,
All right,
they
and then
can't
hop
be.
on to number 4. Number 4, you're starting with a smaller set, so it's not going to be as extreme as this, but it may be as interesting.
Can you really say no to smaller?
Sorry. How's this coming? Whoa, here we go. Let's see.
Kind of the same idea?
All right, so you got 2 elements, and you set in A. So subset and set.
But wouldn't there be a set of?
Oh, you cheated, man. The set itself.
Don't worry, we have them right here.
Yeah. So one detail here.
Oh, yeah.
So you got this element like that, which is saying that
So in the same way, like
this
this one
is a
is so
subset of.
yeah. So like, because like right here we need a double bracket and an A.
Oh,
double
yeah.
bracket.
Yeah.
So we
Yeah.
have like.
Is that true?
If A is a subset of this, yeah, because
That means that every element in here must be an element in here. There's one element in here, which is the letter A. Is the letter A contained in this set?
One more big bracket, yeah.
Yeah, we have one more, right?
I mean, if you look
It's not,
at
right?
set deeper,
Yeah. What's contained in here is
Yeah.
this thing, right? Curly bracket A, curly bracket. So the singleton set of that is a subset. Because this contains one element, which is curly bracket A, curly bracket, and yeah, that's a member of that set. So that is a subset.
okay. So we did have it right here.
So this
So,
really needs to be
set of brackets.
Double
The set containing the singleton set.
I don't like that.
Yeah.
Oh, you're right. Oh, no.
But I see your point.
And then this
But
goes
repeated
from
the
there.
same thing,
Yeah,
yeah.
yeah. So let's look at number 4. Number 4 we're going to talk about as class in a minute. So S is the empty set. So the power set is the set consisting of the empty set. Are there any other elements, any other subsets of this?
Yeah.
No, because it's null.
Okay. Right, so itself is the empty set and they're the same thing. All right, so what are the subsets?
It would be null with the set of null.
Okay, so there's 2 subsets, right? So no, this one's still null, right? That one was correct. But we're looking at subsets of this now. We're down here. And that's got 2 elements.
Now it'd be null.
Yeah, all right. Now go from there to the next one.
Close. Yeah.
Very, very close.
Okay, this is looking
Number 4.
Yeah.
I don't like that.
I think you better curly brackets, that's all I can say.
Yes.
If you want to do it so hand, just
Yeah, that's what I meant. Doesn't look as pretty though.
Okay.
I don't like that.
More elements
I just might do the
Good to know though.
So are we going to go over our subsets of programming in this class, you know? Or
Yeah.
Just your name.
We got 1 subset. So you're
Okay.
I was kind of curious about this, because it's mostly single.
So this should be a set containing 1 element, which is an empty set. So it's really just your curly bracket set.
I figure that one might be needed.
And I think what you had written down was actually the power set of this thing, which has 2 elements, the empty set and the set itself. All right, so you were done with that. Yeah, and then you just gotta get the brackets balanced. Ridiculous is probably good, yeah, yeah. So let's see if you got the idea, and then you can stop. You got the idea. Yes.
We can stop.
Yeah, you say I got out at that point. Cool. Awesome. All right, so you're good to go. Good to go. I'm good to go. All right, cool. So this is a good point to compare notes. So power sets, it's a simple definition, right? But it leads to maybe not so simple things sometimes, which is kind of the nature of the beast. So let's look at the beginning of this Singleton set example. So S equals a singleton set, right? So the power set is going to be a set, and what we're going to list is every subset of S, which is basically the empty set and S, right? But it's more fun if you don't write S, if you actually write out what S is, because it's fun to write curly brackets. So there's the power set of S. Okay, and the power set of the power set, that's the power set of this thing. And I'm just plugging in here. I'm playing a computer, right? Instead of S, I'm just plugging in what S is equal to, which is this set of 2 elements. And so that's going to be a set. I'll put it on a new line. That's going to be a set containing 4 things. Okay, so what are the subsets of this? We know this empty set's always a subset. We know the set itself is always a subset, so curly bracket phi, comma, curly A with 2 closed curlies. That's the power set of S. And then there's 2 singleton sets. There's a set containing just the first element, and then there's the set containing just the second element, which is the singleton set A. So So there's the power set of the power set. And this is the kind of thing a computer has no problem doing, right? You can give it a really absurd problem, and if we gave it problem 4, where we started with the empty set, no problem. It'll just crank this out. It could find the power set of the power set of the power set of the power set, and it would be not confusing at all to it. But to us, this is just mind-boggling, right? Because we're not good at counting lots of curly brackets and keeping things straight in our head. But the concept is exactly the same as what we started with, right? Just list all the things that are subsets of your original set. So to find the next power set, which I'm not going to do because you all did it already, we want to list all the subsets of this thing containing 4 elements. So it's the empty set, it's the set itself, it's all the singleton sets. It's the set containing just these 2 elements, these 2, these 2, these 2, these 2, and all possible combinations, and all the ones that contain 3 elements. If you counted while you were doing this, and some people discovered this on Wednesday when we started talking about subsets, we have this symbol, remember, this is the number of elements in the set. The number of elements in the power set of S is always equal to 2 raised to the number of elements in S. So the singleton has 1 element, the power set will have 2 to the 1 is 2. The power set of that will have 2 to the 2 is 4. The power set of that will have 2 to the 4 is 16 elements. So that's why we got the big long answers for that 4th case. And we're going to prove that about 5 different ways this quarter. And it's all going to tie in to when you did truth tables in Engineering 250. And the fact that if you have n variables, you have 2 to the n rows in that truth table. And if you look for the number of possible truth tables, it's 2 raised to the 2 to the n. That was an old 250 problem. How many 3 input functions are there? So we're going to revisit this in different forms, but this is our first exposure to it. So let's look at question 4, and it's a little easier because we start with an empty set. So the power set of the empty set. And the empty set has 0 things. The power set should have 2 to the 0 is 1 thing, right? And the empty set only has 1 subset, and that's itself, the empty set. And I said Wednesday, every set has 2 subsets. Well, this is true in this case also. It has 2 subsets, the empty set and itself. But those are both the empty set. So we don't get to list elements twice. So that's the whole power set. So the power set of the power set is the power set of the singleton containing phi. And so what are all the subsets of here? Well, there's always the empty set, and there's always the set itself. And in this case, there's no other subsets. And that should probably make you feel good someday, because there's 2 elements in here. There's 1 element in here, and there's 0 elements in here. So 2 to the 0 is 1, 2 to the 1 is 2. 2 to the 2 is 4. So the power set of the power set of the power set is going to have 4 things in it. And 1 is the empty set, and 1 is the set itself. And the other 2 are singleton sets, the set containing the first element and the set containing the second element. Well, the set containing the first element is just phi. The set containing the second element is the set containing phi, so that's this. So does that make sense, at least mechanically? Intuitively, who the heck knows what's going on here? There's something going on. And I think you can actually define integers by working with power sets of the empty set. And you can build up what are called cardinal numbers or ordinal numbers from there. But mechanically, like I say, we can sort of switch off parts of our brain and just pretend we're an automaton and just blindly take the definition and say, okay, we want all the things that are subsets. Just work through them, list them out, and not look back until we're done. And then we can kind of look and be amazed at what we did. All right, questions about that?
Wouldn't all those sets still just be null in the end?
Actually, no. It's a really good question. Bless you. This is not an empty set, right? It's a set containing one thing. The thing it contains happens to be an empty set. But for example, if we took this and we crossed it with a set 1, 2, we would get a collection of tuples, right, where the first element comes from the first set. Well, that's got to be phi. And the second element comes from the second set, so that could be a 1, or it could be a 2. We actually get a set of two things. And if this was actually the empty set crossed with something, which was one of your homework questions, you actually get the empty set, because there's nothing to take from that first set. And there's nothing to pair to make a tuple. There's no tuples in the cross product or Cartesian product, so it's empty. So it contains an empty set, but it itself is definitely not empty. It's got one thing. That's a really interesting thing it has, actually. It's got nothingness, which is like a jar of nothing, kind of hard concept. All right, so this next question set has a bunch of problems on it, but I'm going to say let's skip over all these problems for now, because they're asking you to prove identities, and we're going to talk about membership tables on Monday. But I would like you to go back into groups and think about question 5. But you know what? I made single-sided copies of this, which is not going to work. So I'm going to put this up on the board, or the screen. And I'm going to ask you to play with question 5. And we'll take about 10 minutes to do this, and then we'll go ahead and take a break. The setup here. So we can define properties of sets. An empty set is a set that contains no elements. A finite set is a set that contains a finite number of elements. I'm going to throw a new definition at you, which is a self-consuming set. And the definition is up here. A set is self-consuming if it contains itself. So we've played with sets that contain the empty set and things like that. Suppose we have a set S which contains, maybe a bunch of stuff, but one of the elements of S is S itself. And I'm not saying that's possible. It would be a really weird set that contained itself. But suppose you look at the elements of S, and here's an element, and here's a 5, and here's a tiger, and here's a square, and oh, here's S. That's one of the elements of S. If that happens, we're going to say the set is self-consuming. Okay? So it's just a definition. And most sets are not self-consuming. For example, suppose that T is the set containing 1, 2, 3. Well, this set contains 3 elements. That's the number 1, that's not T. The number 2, that's not T. 3, that's not T. T is not an element of this set. This is not self-consuming. Okay, so you understand the definition? And most sets, not self-consuming, that's okay. Okay, so we're going to define a set B, which contains all sets that are not self-consuming. And then identify 5 elements of that set. And then think about this question. Are there an infinite number of elements in B? And then part D, is B a self-consuming set or not? So let's take about 10 minutes, go back on the boards. I'll make a better display of this in a second. And work through these 4 questions, and let's see where it gets to. Okay, so find a spot of board and start working through these, talk about it, and it's a confusing question, okay, so it's going to take some thought and some discussion. That's an easier one to read.
I said it would be self-consuming if it contains. In other words, if S is in any set.
Yes. Yeah. So
if S is in any set, I'll just do like the universe thing for an example.
So remember, B has to be a collection of sets. Every element of B should be a set. And it's supposed to be a set that's not self-consuming.
Alright.
So is car a set?
oh, all sets then.
Yeah. So it could be a set of all cars.
So then,
Set B. Or a set containing a car.
Well, I think we only need five. Well, it's just saying that this is
would be.
Well, it would be like a set of, like, because B is a set of sets. So we can't just have elements in it, it has to be a set of sets.
So you do like a set of complex, you use like those instead of complex.
So are you trying to define B, or are you working on
Trying to define a
identifying
set
five
B.
elements? Okay. And I can give that to you.
And complex
So how about this? B is the set of all S such that S is not an element of S.
Okay.
Which is where I think you were heading, but I think you were using B inside as well as outside.
Yeah. The element
that's like
S
was
was
there an infinite number of elements in B?
is not.
And
Yeah.
this
So
doesn't.
you can see any reason with the.
Alright, so it's
That's
those are definitely elements of the set five elements, but there's probably more elements in B also, right? So it definitely includes A, C, and D.
This is equal to this, but this is not.
Yeah.
Well, S is any.
So for listing identifying any elements of the set, yeah, you've got that there already.
But it's not.
And
So B would be like S plus 1,
all right,
S
cool.
plus 2,
Um,
S minus
you
1,
do a Q.
Or
S
just
minus
like,
2.
we wouldn't necessarily have to define.
S
What would be dot dot dot?
divided by
All sets
Yeah.
that are self-consuming.
Something like that.
Sure.
Because that set won't be able to consume itself. Right?
Infinite number of elements in B. Well, yeah. And what would there is sets that aren't. Because like a power.
Yes,
set is
there
still
would
a
be.
set that doesn't contain itself on
Because whatever you plug in for S changes anything. Depending on what S may be. Right?
Is B a self-consuming set or is it not? That's the paradox. Because it is.
So we might have to write like C and then. We have to
Because if it
Well,
doesn't.
if S can't equal S, wouldn't that just equal null?
It is a set.
It's saying S is not contained in S.
Oh, S is not contained in S.
Yeah, so S is a set,
Mhm.
right? And this is saying we want it sets that don't contain the element S.
And
So, but what does S plus 1 mean?
essentially,
So,
yeah, to make it not S essentially. I thought it was more of an element more so on that, but it's the set, right?
So can you think of a set that you could just define in curly brackets that wouldn't be self-consuming?
Null.
Yeah, a null set doesn't contain itself, it doesn't contain anything.
Mm-hmm.
So null is definitely not self-consuming, so that's an element of B.
So the set of null?
That would also be not self-consuming.
I'll do those two.
What about the set of integers?
Oh, yeah, I guess.
Does that contain, does that include the set of integers?
It would, I guess.
So what are some of the things that you find in the set of integers? What are some of the elements?
Just general numbers of integers.
Like?
I mean, that's a good
3.
3. Okay, that's an element of Z. What else?
A B? Or a Z? Oh,
In the set of integers.
okay.
So it's got the element 3. What
Mhm.
else? Just rattle off like 5 elements of Z.
Well, I
Okay.
guess at that point, it would no longer be, yeah.
Kind of like that.
But, so name 5 elements of the set of integers. Just like out loud. What are 5 integers? 1, 2, 3, 4, 5. Perfect, right? Those are all elements of Z.
Okay.
Right? So is 17, so is negative 500, so is 0. We could sit here and we could name elements of the set of Z
To
all
infinity.
day, right? And no matter how long we do that, are any of us ever going to say Z is an integer?
No.
No, because Z is a set. It's not an integer.
So the set of Z.
of all.
So Z itself does not contain itself.
That it would be
So Z, even without the curly brackets outside, just Z by itself is not self-consuming.
And
Right.
so would.
And same with Q, exactly. And same with the positives. Right? So those are all good examples, perfect examples of sets that are not self-consuming. So we know that B contains at least those 5 things. If I had said identify 500 elements of B, you could probably do that too, right?
Yeah.
If you had enough time and a big enough
I don't think we
whiteboard.
could put alphabet because the letters in the alphabet are in alphabet.
Suppose
Unless
you have
there's a
set
specific
containing
symbol.
A through Z,
Yeah,
right?
set.
26 elements does not contain the set A
unsolvable,
through Z.
like deemed unsolvable,
Yeah.
like $1 million if you solve it.
So if you had to do this for the rest of eternity, could you keep naming sets that aren't contained in themselves?
Yeah, I guess you
Yeah,
could.
you definitely
Periodic
could.
table itself would be
Yeah.
another example.
So are there an infinite number of elements in B? Yeah.
Yeah.
Okay. So now think about question D.
You know what I mean? Like, just people are trying to figure it out. So.
Be a self-consuming set or not self-consuming set.
Make sure you get the
In other words, if S is in any set.
explanations in our head, but we didn't put it down.
Okay, what's your...
Yeah, it would be.
Well, it would
in-
be.
it would be
Like,
self-consuming,
we could
wouldn't
just-
it?
We could just.
Because
like,
no matter,
set of
it really
integers,
depends on
just do the
perspective more
power
so,
set
like
over
depending
and
on
over
what you're
again,
grouping
not
together.
the-
If you're grouping together
But
groups
then for the
or
self-consuming
things that could
part,
be
it's
anything like
paradox,
that,
like, we can't do it, that's the
then-
Okay.
part, because if it is a self-consuming set, then it
You know, I'm
won't
off
be
at
in
least.
this power set, or in this set, because it is self-consuming.
Right.
But then it would be kind of wasn't
since,
self-consuming.
yeah, it would be self-consuming since it's, you know, nigh infinite of whatever you can assume is not self-including.
Thinking about D? Yeah. What are you thinking?
Essentially, B could be in a set of something else.
Could be both.
And we can just loop back around to
So
numbers,
the trick is we've got a definition for what it means to be self-consuming.
you know?
That's a kind of binary thing. It either is or it isn't.
You want
If it isn't, then it is. And if it is,
I
then
hate
it
this,
isn't.
but
Or if it isn't, then
made a
it's
program, not create a black hole on a whiteboard.
So what are you thinking, yes?
Yeah, I'm thinking it's technically a self-consuming set. I mean, really just, okay, it literally can be both. It just determines on what angle you look at it. Because a set of infinite sets, essentially, whatever group you want to look at, you can always group something into something no matter what you do.
Okay, so let's talk about B. So is B self-consuming? So we know what the definition is, right? We've got that in our minds. So S is self-consuming if S is contained in S. B is the set of all sets that are not contained in themselves, sets that are not self-consuming. Okay, so question, is B self-consuming? Well, when mathematicians want to answer a question that's true or false, one way to do this is to assume it's true and see what happens. If you assume something is true and you end up with a contradiction, that will prove that the thing was not true. Because if it's true, then we get a contradiction, right? So assume something's true, and if it turns out that following from that, you've proven I'm the Queen of England, right? Assuming I'm not the Queen of England, that thing must not have been true to begin with, because it would lead you to a false statement. So let's assume, I don't know, should we assume it's self-consuming or not self-consuming? Most things are not self-consuming, so let's assume B is not self-consuming. Doesn't matter which one we start with. Well, if B is not self-consuming, then B is not contained in itself. Well, this up here is the set of all sets that are not contained in themselves, and B is a set that's not contained in itself. So B is contained in the set of all S that don't contain themselves, which is the set B. So if B is not self-consuming, then B is contained in B, so B is self-consuming. And that's a contradiction. If B is not self-consuming, it's self-consuming. So contradiction, I'll write with a sideways number sign. Right? If this is a pen, then this is not a pen. That's effectively what we just proved. That's absurd. So B must be self-consuming, because we've proven this can't be true. So B must be self-consuming. Well, if B is self-consuming, that means B is contained in B, because that's the definition of self-consuming. Well, B is a set of all things that are not contained in themselves. We just showed that B is contained in B, which means B is not contained in this set up here. So we know that B has to be self-consuming, which means B is contained in B, but from that we know that B is not contained in B. And that's absurd also. Because if you take any set and you pick anything X, either X is in that set or it's not in that set. It's a binary condition. And we've just shown that if B is in B, then B is not in B, and that's absurd. So this can't be true either. So we've shown that B cannot be non-self-consuming, and it also cannot be self-consuming. So what is it? It's a paradox. And it's a paradox that arises because we started with this idea on day one that a set is a collection of things. And that's something that we can call naive set theory. It's set theory that we get by starting with this sort of vague, loose, intuitive notion of a set as just a collection of stuff. And because we're allowing sets to potentially contain themselves, we can get into paradoxes like this. So this was solved 100-some years ago by the development of what's called axiomatic set theory, which is a very rigorous form of set theory that starts with a fixed set of axioms that rigorously defines things like what is a set and what do we mean by these set operations. And for us in this course, naive set theory is perfectly fine. We don't need to get fancy, but we need to be aware that there are possible paradoxes in what we're doing, because we are being a little fast and loose with the definitions of what a set is. But it's going to be fine for everything we have to do. But it's an interesting fact that there is this paradox that comes from a fairly simple definition. All right, so let's take a few minute break. Come back at 1:30. We'll talk about Hilbert's Grand Hotel and see what that's all about.